Subscribe to the channel so you don't miss out on any of these videos. The universe has always been a mystery, a vast expanse of space filled with phenomena we're only just beginning to understand. But imagine this, a time when the entire cosmos was wrapped in darkness. No stars, no galaxies, just an endless void. Then, suddenly, light pierces through, marking the birth of stars and galaxies, transforming the universe forever. This wasn't just the beginning of starlight as we know it. It was the moment that shaped the very structure of the cosmos. The story of how this happened is one of the most captivating mysteries of space, and it's what we call the era of reionization. What exactly was this era, and why is it so important? To understand, we have to go back over 13 billion years, to a time shortly after the Big Bang. The universe was still in its infancy, filled with a dense, hot soup of particles, protons, neutrons, electrons, all whizzing around in chaos. It was so hot that atoms couldn't form. Electrons were free to move, scattering light and making the universe opaque. But as the universe expanded and cooled, something incredible happened. Atoms began to form. This marked the end of the primordial fog, allowing the universe to become transparent for the first time. This phase, known as recombination, led to what scientists call the Dark Ages of the universe. During the Dark Ages, there was no light source to illuminate the vast expanse. The only radiation that existed was left over from the Big Bang, stretched out into faint microwaves we can still detect today as the cosmic microwave background, CMB. For millions of years, the universe remained dark and cold, an eerie, silent void. But this wasn't the end of the story. It was the calm before one of the most transformative eras in cosmic history. Now, here's where things get exciting. At some point, gravity began to work its magic. Tiny clumps of matter, left over from the Big Bang, started to come together. These clumps grew larger, pulling in more and more material. Eventually, under immense pressure, nuclear fusion ignited, and the first stars were born. These stars weren't like the stars we see today. They were massive, short-lived, and incredibly bright. They burned with such intensity that they released vast amounts of ultraviolet radiation, powerful enough to ionize the hydrogen gas around them. This process, where ultraviolet light from the first stars stripped electrons from hydrogen atoms, is what we call reionization. Before this, most of the hydrogen in the universe was neutral, meaning it had a proton and an electron bound together. But the energy from these early stars shattered that bond, turning the hydrogen into free protons and electrons once again. The universe, once shrouded in darkness, began to glow. But here's the twist. This wasn't an instant transformation. Reionization didn't happen all at once. It was a gradual process, stretching over hundreds of millions of years. As more stars formed, and later galaxies, their combined light ionized larger and larger regions of space. These regions grew like bubbles, eventually overlapping until the entire universe was reionized. Why does this matter? Well, reionization didn't just light up the universe, it fundamentally changed its structure. The energy from the first stars and galaxies affected how matter clumped together, shaping the cosmic web of galaxies and dark matter we see today. Without reionization, the universe might look very different, or it might not have evolved to support life at all. Now, let's dig deeper into the science. One of the most intriguing aspects of the era of reionization is how it connects to the first galaxies. These early galaxies were nothing like the grand spiral or elliptical galaxies we see now. They were small, irregular collections of stars, gas, and dark matter. But they were incredibly efficient at producing light, thanks to their high rates of star formation. Astronomers believe these galaxies played a crucial role in completing reionization, as their combined light had the power to ionize vast stretches of the universe. Yet, many questions remain. For example, what were the first stars made of? Scientists refer to them as population 3 stars, a name that might sound ordinary but hides their extraordinary nature. These stars were formed from primordial gas, hydrogen and helium created during the Big Bang, with virtually no heavier elements. This made them incredibly massive, sometimes hundreds of times the mass of our Sun, and very short-lived. They burn out in just a few million years, exploding as supernovae and scattering heavier elements across the cosmos. These elements, in turn, would seed the formation of the next generation of stars and planets, including the very materials that make up Earth and even us. The evidence for the era of reionization comes from a variety of sources, each adding a piece to the puzzle. One of the most important is the cosmic microwave background. By studying tiny variations in this ancient radiation, scientists can infer the conditions of the early universe and how reionization unfolded. Another critical source is the light from distant quasars, supermassive black holes surrounded by glowing disks of gas. As this light travels through space, it passes through clouds of hydrogen, which leave telltale absorption lines in the spectrum. These lines reveal whether the hydrogen is neutral or ionized, providing a snapshot of the universe during reionization. But here's where things get tricky. Observing this era directly is incredibly difficult. The light from the first stars and galaxies is faint and redshifted, stretched to longer wavelengths by the expansion of the universe. It's only with cutting-edge telescopes, like the James Webb Space Telescope, JWST, that we're beginning to glimpse these ancient objects. Even so, there's much we don't know. For instance, what exactly caused reionization to end? Was it primarily the light from stars, or did other sources, like black holes, play a significant role? One of the most fascinating aspects of the era of reionization is its connection to the large-scale structure of the universe. During this period, the interplay between light and matter created patterns that would persist for billions of years. These patterns, known as the cosmic web, consist of filaments of galaxies and dark matter separated by vast voids. Understanding how reionization shaped this structure could answer some of the biggest questions in cosmology, like how galaxies form and evolve. The story of reionization isn't just about the past, it's also about the future. By studying this era, we're learning about the conditions that led to the formation of stars, galaxies, and planets. We're uncovering the processes that made life possible and gaining insight into how the universe might evolve in the billions of years to come. This transformation of the universe during the era of reionization was a turning point, but it's also one of the most enigmatic periods in cosmic history. Think about it, we're trying to piece together a puzzle from over 13 billion years ago, with only faint and scattered clues to guide us. Despite groundbreaking discoveries, there's so much we still don't know. What exactly triggered the birth of the first stars? Why did they form when they did? And how did their energy interact with the surrounding hydrogen to reionize the universe on such a massive scale? One key aspect of the era of reionization is the role played by ultraviolet radiation. This high-energy light was crucial for ionizing hydrogen, but it wasn't just a one-way process. As ultraviolet light traveled through space, it was absorbed and scattered by the neutral hydrogen around it. This created a sort of cosmic tug-of-war. As stars and galaxies produced more ultraviolet light, they slowly chipped away at the dense, neutral hydrogen, creating ever-expanding ionized bubbles. Over millions of years, these bubbles grew larger and began to merge, forming networks of ionized regions. It was a slow, uneven process, with pockets of neutral hydrogen lingering for some time before being completely reionized. To picture this, imagine shining flashlights in a dark room filled with fog. At first, the light only reaches small, localized areas. But as more flashlights turn on and their beams overlap, the room gradually becomes clearer. This is similar to how the first stars and galaxies illuminated the universe, gradually clearing the cosmic fog and bringing the universe into the light. Another critical piece of this puzzle is the interplay between stars and their environments. The first stars were so massive and hot that they didn't just emit ultraviolet light. They also released powerful stellar winds and ended their lives in explosive supernovae. These events injected huge amounts of energy into their surroundings, heating and ionizing the gas while also dispersing heavier elements like carbon and oxygen. This process, known as metal enrichment, was essential for forming the next generation of stars and galaxies. Without it, the universe might never have developed the complexity needed to sustain life. But reionization wasn't just driven by stars. Galaxies also played a crucial role, especially the small, faint ones that are difficult to detect even with today's advanced telescopes. These so-called dwarf galaxies might have contributed more to reionization than their larger counterparts, simply because there were so many of them. Their combined light could have been enough to ionize vast regions of the universe, even if individual galaxies weren't particularly bright. Interestingly, there's also evidence that black holes contributed to reionization. As matter spiraled into these massive objects, it heated up and emitted intense X-rays. These X-rays could travel much farther than ultraviolet light, ionizing gas over larger distances. While black holes likely weren't the primary drivers of reionization, they added another layer of complexity to this era, influencing the way energy and matter interacted across the cosmos. One of the most challenging aspects of studying the era of reionization is the vast time scales involved. This period likely began around 400 million years after the Big Bang and lasted for several hundred million years. During this time, the universe underwent dramatic changes, transitioning from a dark, neutral state to a bright, ionized one. Understanding these changes requires not only observing distant galaxies but also creating sophisticated simulations to model how light, matter, and gravity interacted on cosmic scales. These simulations are incredibly complex, incorporating everything from the formation of stars and galaxies to the physics of radiation and gas dynamics. By comparing the results of these simulations with actual observations, scientists can refine their models and gain deeper insights into how reionization unfolded. For example, they've discovered that reionization wasn't a uniform process. It varied depending on the density of matter in different regions of the universe. Denser areas, which had more stars and galaxies, likely reionized first, while less dense regions lagged behind. Another fascinating aspect of this era is how it set the stage for the cosmic web, the large-scale structure of the universe. During reionization, the interactions between light and matter helped shape the distribution of galaxies and dark matter, creating the intricate networks of filaments and voids we see today. This structure isn't just a random arrangement. It's a direct result of the physical processes that occurred during the era of reionization. By studying this structure, we can learn more about the forces that governed the early universe and continue to shape it today. One of the most groundbreaking tools for studying this era is the 21 cm hydrogen line, a specific wavelength of light emitted by neutral hydrogen atoms. By observing this signal, scientists can map the distribution of hydrogen during reionization, providing a detailed picture of how the universe transitioned from darkness to light. This technique has the potential to revolutionize our understanding of the early universe, revealing details that are impossible to see with traditional telescopes. Despite all these advances, there are still major unanswered questions. For instance, why did reionization end when it did? Did something specific trigger its conclusion, or was it simply the natural result of the universe's evolution? And what role did different types of galaxies and black holes play in this process? These questions drive ongoing research, pushing the boundaries of what we know about the cosmos. The era of reionization is more than just a chapter in the history of the universe. It's a window into the processes that shaped everything we see today. From the first stars and galaxies to the cosmic web and beyond, this era set the stage for the universe as we know it. And as we continue to explore its mysteries, we're not just learning about the past, we're uncovering the fundamental laws that govern the universe itself. The era of reionization wasn't just a singular event, but a transformative epoch that bridged the gap between the darkness of the cosmic, dark ages, and the structured, vibrant universe we inhabit today. As we dive deeper into the mysteries of this time, we begin to appreciate how interconnected the various elements of the cosmos truly are. It's a story of light overcoming darkness, order emerging from chaos, and complexity blossoming from simplicity. Let's continue peeling back the layers of this profound chapter in cosmic history. One of the defining features of reionization was its patchy, uneven nature. Unlike a switch flipping on all at once, reionization happened in stages, and its progress was anything but uniform. The early universe was a tapestry of neutral hydrogen regions interspersed with glowing ionized bubbles. These bubbles, created by the energy output of young stars and galaxies, slowly expanded over millions of years, eventually merging to form vast ionized networks. This process wasn't random. It was deeply influenced by the underlying distribution of matter in the universe. The cosmic web, a sprawling network of filaments and voids shaped by dark matter and baryonic matter, acted as a scaffolding for this process. Denser regions of the web, where galaxies were forming, became hotspots for reionization. The light from these regions spread outward, gradually eroding the neutral hydrogen in less dense areas. However, this wasn't a one-sided process. As the ionized regions expanded, they encountered pockets of dense gas that were harder to penetrate. These dense regions acted like barriers, slowing the progress of reionization and creating a highly non-uniform ionization front. To understand this better, let's consider the role of feedback mechanisms during reionization. Early stars, known as population 3 stars, were unlike any stars we see today. These stars formed from pristine hydrogen and helium, with no heavier elements to cool the gas during their formation. As a result, they were incredibly massive, often tens or even hundreds of times the mass of our Sun. These massive stars burned through their nuclear fuel quickly, producing immense amounts of ultraviolet light and ionizing radiation. However, the intense radiation from these stars also heated the surrounding gas, making it more difficult for new stars to form in nearby regions. This is known as radiative feedback, and it played a crucial role in regulating star formation during the era of reionization. While the first stars were instrumental in kickstarting reionization, their feedback effects created a delicate balance, preventing the process from spiraling out of control. Adding another layer of complexity were the galaxies themselves. Modern observations suggest that the majority of ionizing photons during reionization came not from massive galaxies, but from smaller, fainter ones. These dwarf galaxies were abundant and efficient producers of ultraviolet light, even if their individual contributions were modest. Their combined output created a cumulative effect that was instrumental in driving reionization forward. But here's where things get even more interesting. Not all the ionizing photons produced by these early galaxies actually escaped into the intergalactic medium, IGM. A significant fraction of this light was absorbed by gas and dust within the galaxies themselves. This concept, known as the escape fraction, is a critical variable in understanding reionization. High escape fractions mean that more photons can ionize the IGM, accelerating reionization. Low escape fractions, on the other hand, would slow the process down, requiring more time or more sources of ultraviolet light to achieve the same level of ionization. Then there's the matter of black holes. While the first stars and galaxies were the primary architects of reionization, black holes, specifically, the accreting black holes at the centers of early galaxies, also played a role. As matter spiraled into these black holes, it released enormous amounts of energy in the form of X-rays. Unlike ultraviolet light, X-rays are less easily absorbed by neutral hydrogen, allowing them to travel farther and ionize gas over larger volumes of space. This raises an intriguing question. How much of reionization was driven by these energetic processes versus the steady output of ultraviolet light from stars? It's a question that astronomers are still working to answer, and it highlights the complexity of the reionization era. Multiple sources of energy, interacting on different scales and timescales, contributed to this cosmic transformation. To study these phenomena, astronomers have turned to some of the most advanced tools ever built. The James Webb Space Telescope, JWST for instance, is designed to peer deep into the universe, capturing light from some of the earliest galaxies. By studying these faint, ancient objects, scientists can learn more about the stars, galaxies, and black holes that powered reionization. Early results from JWST have already revealed surprises, including the discovery of surprisingly massive galaxies forming much earlier than expected. These findings challenge existing models of galaxy formation and suggest that we may need to rethink our understanding of the early universe. Simultaneously, radio telescopes like the Hydrogen Epoch of Reionization Array, HERA, are providing complementary insights. By detecting the faint 21 cm signal emitted by neutral hydrogen, these telescopes can map the distribution of hydrogen during reionization, offering a direct view of how ionization progressed over time. Combining these observations with theoretical models and computer simulations allows astronomers to create a more complete picture of this enigmatic era. And yet, for all our progress, reionization remains a frontier of discovery. Why, for example, did the universe transition from neutral to ionized when it did? Was there a specific tipping point, or was it simply the natural outcome of star and galaxy formation? And how did the interplay between light and matter shape the cosmic structures we see today? These are questions that continue to drive research, pushing the boundaries of what we know about the universe. As we unravel these mysteries, one thing becomes clear: the era of reionization isn't just a story about the past. It's a story about the processes that shape the universe we see today. From the formation of the first stars and galaxies to the intricate interplay of light and matter, this epoch set the stage for everything that followed. And as we look deeper into the cosmos, we're not just exploring ancient history, we're uncovering the fundamental laws that govern the universe itself. The era of reionization also serves as a reminder of how interconnected cosmic processes truly are. This was not an isolated event but a culmination of processes that had been building since the universe's inception. To fully grasp its significance, it's essential to step back and consider the broader timeline of cosmic evolution. The story begins with the Big Bang, around 13.8 billion years ago. In its immediate aftermath, the universe was a hot, dense soup of particles, protons, neutrons, and electrons, floating in a sea of energy. As the universe expanded, it cooled, allowing these particles to combine and form the first atoms, primarily hydrogen and helium. This period, known as recombination, marked the moment when the universe became transparent to light, releasing what we now detect as the cosmic microwave background radiation, CMB. However, while the CMB gave the universe its first visible signal, it was far from illuminating in the sense of visible light. The cosmos then entered the so-called Dark Ages. During the Dark Ages, the universe was a vast expanse of neutral hydrogen, absorbing most light and rendering the cosmos largely invisible to any external observer. Without stars or galaxies, there was no source of illumination, only the faint glow of the CMB. These were the formative years, a time when small fluctuations in the density of matter began to grow under the influence of gravity. These tiny irregularities, captured in the patterns of the CMB, served as the seeds for all future structures. Over time, gravity worked its magic, pulling matter together into denser regions. As these clumps of matter grew, they formed the first halos of dark matter, structures that would eventually host galaxies. Within these halos, gas cooled and condensed, leading to the birth of the first stars. These population 3 stars were different from the stars we know today. Their lack of heavier elements made them uniquely massive, short-lived, and extraordinarily luminous. These were the cosmic pioneers, the first objects to pierce the darkness with their light. The light from these stars wasn't just a beacon, it was transformative. The ultraviolet radiation emitted by population 3 stars began to ionize the surrounding hydrogen gas, stripping electrons from protons and creating regions of ionized gas. This marked the beginning of reionization, a process that would continue for hundreds of millions of years. However, the light from these stars alone wasn't sufficient to reionize the entire universe. Their lifespans were too short, and their numbers were too few. Something more was needed. Enter the first galaxies. As star formation continued, small galaxies began to form, clustering together in larger structures. These early galaxies were incredibly efficient at producing ultraviolet light, which further drove the reionization process. The interplay between these galaxies and the intergalactic medium created a dynamic environment where regions of ionized and neutral gas coexisted, slowly tipping the balance toward a fully ionized universe. But the process wasn't smooth or straightforward. The interaction of light and matter during reionization created a highly complex landscape. Dense pockets of gas, such as those in the cores of nascent galaxies, were harder to ionize and acted as shields, slowing the spread of ionization fronts. At the same time, the competition between star formation and feedback processes added another layer of complexity. The intense radiation and supernova explosions from early stars often disrupted the gas in their vicinity, suppressing further star formation in some areas while triggering it in others. Another fascinating aspect of the reionization era is the role of dark matter. While dark matter itself doesn't emit or absorb light, its gravitational influence was crucial in shaping the large-scale structure of the universe. The distribution of dark matter dictated where galaxies formed and how they clustered together, indirectly influencing the progress of reionization. Regions with higher concentrations of dark matter became the first hubs of star formation and ionization, creating a patchwork pattern of light and darkness across the universe. Astronomers have been able to reconstruct much of this story thanks to cutting-edge observations and simulations. One of the key tools in this endeavor is the study of quasars, the bright, energetic cores of distant galaxies powered by supermassive black holes. Quasars act as cosmic lighthouses, their light traveling vast distances and interacting with the intervening gas along the way. By analyzing the absorption patterns in quasar light, scientists can map the distribution of neutral and ionized hydrogen, providing a window into the state of the universe during reionization. In addition to quasars, the discovery of early galaxies has been instrumental in advancing our understanding. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have pushed the boundaries of what we can observe, revealing galaxies that formed less than a billion years after the Big Bang. These observations have provided crucial insights into the types of stars and galaxies that existed during the reionization era, as well as their contribution to the ionizing photon budget. Computer simulations have also played a vital role in piecing together the puzzle of reionization. By combining the laws of physics with observational data, researchers can create detailed models of how the universe evolved during this time. These simulations allow scientists to test different scenarios, explore the effects of various parameters, and gain a deeper understanding of the complex interplay between stars, galaxies, and the intergalactic medium. Despite these advances, many questions remain unanswered. For instance, what was the exact timeline of reionization? Did it happen uniformly across the universe, or were there regional variations? How did the properties of early stars and galaxies evolve during this period? And what role did less conventional sources, such as black holes and exotic particle interactions, play in shaping the reionization process? These mysteries continue to drive research, pushing the limits of what we can learn about the early universe. Ultimately, the era of reionization is more than just a chapter in cosmic history. It's a story of transformation, a testament to the power of light to overcome darkness, and a reminder of the intricate processes that govern the universe. By studying this epoch, we not only learn about the past but also gain insights into the fundamental principles that continue to shape the cosmos. The era of reionization encapsulates one of the most profound transformations in the history of the cosmos. It marked the transition from a universe dominated by darkness and neutral hydrogen to one filled with radiant light and ionized gas. This was the era when the seeds of modern galaxies were sown, when the fundamental structure of the universe began to take shape, and when light became a dominant force, transforming not just the universe's physical state but its potential for hosting complex structures like galaxies, stars, and eventually planets. As we continue to unravel the mysteries of reionization, the role of early galaxies takes center stage. These galaxies were vastly different from the ones we see today. For one, they were significantly smaller and more chaotic, often appearing as clumps of stars without the orderly spiral or elliptical shapes we're accustomed to. Their stars, predominantly population 3 stars, were massive and burned at exceptionally high temperatures. These stars likely contributed the majority of ultraviolet photons needed to ionize the surrounding hydrogen gas. But what makes these galaxies so intriguing is their rapid evolution. Despite their small size, they underwent periods of intense star formation, outshining even some modern galaxies relative to their mass. An essential question that scientists have long grappled with is how these galaxies sustained their star formation. In today's universe, star formation is often regulated by a delicate balance between the cooling of gas and the feedback processes from stars and black holes. In the early universe, this balance was skewed. The lack of heavy elements meant that the cooling mechanisms were limited, yet the gravitational pull of dark matter halos provided a sufficient reservoir of gas. These conditions created a feedback loop where the radiation from newly formed stars triggered further star formation, while simultaneously limiting it in nearby regions through heating and gas expulsion. But galaxies alone weren't the only players in reionization. Another critical contributor was the intergalactic medium, IgM, the vast expanses of gas that filled the spaces between galaxies. During the Dark Ages, the IgM was primarily neutral hydrogen. As the first stars and galaxies formed, their ultraviolet light began to ionize pockets of this gas, creating bubbles of ionized hydrogen. Over time, these bubbles grew and merged, eventually permeating the entire universe. The study of the IgM during this transition offers unique insights into the reionization process, particularly through the phenomenon of the Lyman alpha forest. The Lyman alpha forest refers to the absorption lines in the spectra of distant quasars, caused by neutral hydrogen in the IgM. As light from quasars travels through the universe, it interacts with the intervening hydrogen, creating a series of absorption features. By analyzing these features, scientists can map the distribution and state of hydrogen during reionization. For example, regions with dense neutral hydrogen create strong absorption, while ionized regions allow the quasar light to pass through more freely. This technique has been instrumental in pinpointing the end of reionization, roughly a billion years after the Big Bang. Yet, reionization wasn't a uniform process. It's believed to have occurred in a patchy manner, with different regions of the universe ionizing at different rates. This patchiness is thought to have been influenced by the distribution of galaxies, the density of the IgM, and the clustering of dark matter. Some regions, particularly those near dense clusters of galaxies, would have ionized more quickly, while others, further away from sources of ultraviolet radiation, lagged behind. This uneven progression adds another layer of complexity to our understanding of the era. Adding to this complexity is the role of less conventional sources of ionizing radiation. While stars and galaxies were the primary drivers, other phenomena may have contributed. For instance, quasars and active galactic nuclei (AGN), powered by supermassive black holes, are known to emit intense ultraviolet and X-ray radiation. Although their overall numbers were lower during reionization, their immense luminosity could have had a disproportionate impact on the surrounding gas. Similarly, the decay or annihilation of exotic particles, such as dark matter candidates, might have provided additional sources of ionization, although this remains speculative. One of the most compelling aspects of reionization is its broader implications for cosmic evolution. The end of reionization marked the beginning of the modern universe, where light could travel freely and galaxies could interact with their surroundings without the constraints of neutral hydrogen. This freedom allowed for the growth of larger structures, the formation of galaxy clusters, and the eventual development of the cosmic web, a vast network of galaxies and dark matter that defines the large-scale structure of the universe. The cosmic web itself is a product of the interplay between gravity and the ionization state of the universe. During reionization, the heating of the IgM by ultraviolet radiation caused it to expand, smoothing out smaller density fluctuations while preserving larger ones. This process helped to define the boundaries of the web, shaping how galaxies are distributed today. The regions of the universe that were more densely populated during reionization became the nodes of the web, connected by filaments of gas and dark matter, while voids formed in less dense areas. Despite the wealth of knowledge we've gained, the era of reionization remains one of the most challenging periods to study. The faintness of early galaxies, combined with the scattering of light by the IgM, makes direct observations incredibly difficult. The James Webb Space Telescope has already made significant strides in overcoming these challenges, capturing some of the most distant galaxies ever observed and shedding light on their properties. But even with these advances, many questions remain. What were the precise mechanisms that drove reionization? How did the interplay between galaxies and the IgM evolve over time? And what role did less conventional processes play in shaping the era? Understanding reionization is not just about looking back, it's also about looking forward. By studying the conditions that led to the first light, we gain insights into the processes that continue to shape the universe. The same principles that govern star formation, feedback, and the interaction of light and matter during reionization are still at play today, albeit in a more evolved context. This continuity highlights the interconnectedness of cosmic history, where each epoch builds on the foundations of the one before. The study of reionization also offers profound implications for our understanding of cosmic origins and the potential for life in the universe. During the Dark Ages and the era of reionization, the universe was laying down the groundwork for everything we see today. The formation of the first stars not only brought light but also began the process of chemical enrichment. These early stars, predominantly composed of hydrogen and helium, forged heavier elements like carbon, oxygen, and nitrogen in their cores through nuclear fusion. When these stars reached the end of their lifespans and exploded as supernovae, they scattered these elements into space, enriching the surrounding gas clouds. This chemical enrichment process is crucial because these elements are the building blocks of planets and life. Without the metals created during and after the era of reionization, rocky planets like Earth would not exist. The conditions that arose during this era also set the stage for the subsequent evolution of galaxies, including the eventual formation of the Milky Way. Understanding this process provides a glimpse into how common or rare the conditions for life might be in the universe. Another intriguing aspect of the era of reionization is the timeline of events that led to the ionization of the universe. While we know that reionization ended roughly 1 billion years after the Big Bang, its beginning is less well defined. Some models suggest that the first stars formed as early as 100 million years after the Big Bang, while others place this event slightly later. Pinpointing this timeline is one of the key challenges in studying the era, as it directly relates to the efficiency and speed of the processes involved. The cosmic microwave background (CMB) provides some critical clues about the timing of reionization. This faint glow of radiation, a remnant from the Big Bang, carries imprints of the universe's early conditions. By studying the polarization of the CMB, scientists can infer when the universe transitioned from being neutral to ionized. These observations, combined with the data from telescopes like the James Webb and others, allow researchers to build a more complete picture of how reionization unfolded. Adding another layer of complexity to the study of this era is the role of dark matter. While dark matter does not interact with light, and thus does not directly contribute to reionization, it played an indirect but vital role in shaping the process. The gravitational pull of dark matter halos provided the scaffolding for the formation of the first galaxies. Without these dense regions of dark matter, the gas required for star formation would not have been able to collapse and cool efficiently. This interplay between dark matter and baryonic matter is another key area of research, as it connects the unseen components of the universe with the luminous structures we observe. The challenges of observing the era of reionization stem from the vast distances involved. Because light from this period has traveled billions of years to reach us, it is incredibly faint and redshifted. This redshift, caused by the expansion of the universe, stretches the wavelengths of light, pushing it into the infrared spectrum. Instruments like the James Webb Space Telescope, which is designed to observe in the infrared, are uniquely suited to studying these early galaxies. However, even with advanced technology, the faintness of these objects means that every piece of data is precious, and the interpretation of this data requires careful analysis and modeling. One of the most exciting areas of research in this field is the search for gravitational lensing effects. Gravitational lensing occurs when the light from a distant galaxy is bent and magnified by the gravity of a massive foreground object, such as a galaxy cluster. This natural magnification allows astronomers to observe galaxies that would otherwise be too faint to detect. By using gravitational lensing, scientists have been able to peer deeper into the universe than ever before, uncovering some of the earliest galaxies and their properties. These observations have revealed that the first galaxies were remarkably efficient at producing ultraviolet light, much more so than their modern counterparts. This efficiency was likely due to their high star formation rates and the lack of heavy elements, which made their stars burn hotter and brighter. However, the exact mechanisms that govern these processes are still a matter of debate. Did these galaxies form their stars in bursts, with periods of intense activity followed by quiescence? Or was their star formation more continuous and sustained? Answering these questions requires a combination of observations and simulations. Cosmological simulations are another critical tool in studying reionization. By using supercomputers to model the universe's evolution, scientists can test different scenarios and compare them to observations. These simulations incorporate the physics of dark matter, gas dynamics, star formation, and feedback processes, creating virtual universes that help us understand the real one. They have shown that reionization was likely a self-regulating process, where the ionizing radiation from stars and galaxies both drove and limited star formation in different regions. One surprising finding from simulations and observations is the role of small galaxies in reionization. While the largest and brightest galaxies receive much of the attention, it is now believed that smaller, faint galaxies contributed the majority of the ionizing photons. These galaxies, often too faint to observe directly, were numerous enough to have a significant collective impact. Their role highlights the importance of studying the full range of galaxy populations to understand reionization fully. The end of reionization was a turning point for the universe. As the last pockets of neutral hydrogen were ionized, the universe became transparent to ultraviolet light, allowing it to travel freely across vast distances. This transparency not only made it possible for us to observe distant galaxies today but also allowed galaxies to interact with their surroundings in new ways. The ionized intergalactic medium provided a less hostile environment for the growth of galaxies, enabling the formation of more complex structures over time. Reionization also had implications for the subsequent growth of supermassive black holes. During this era, the first black holes formed from the remnants of massive stars. As gas accreted onto these black holes, they grew in size and began to emit intense radiation. This radiation contributed to reionization while also influencing the surrounding gas and galaxies. The interplay between black holes and their environments is a key area of study, as it connects the small-scale processes of star and black hole formation with the large-scale evolution of the universe. The presence of supermassive black holes during the era of reionization raises one of the most perplexing questions in modern astrophysics. How did these black holes grow so rapidly? Observations have revealed quasars, galaxies with actively feeding supermassive black holes, that existed less than 1 billion years after the Big Bang. For these black holes to reach such enormous masses in such a short time, they must have either formed from very large seed black holes or experienced extraordinarily efficient growth. Both scenarios are challenging to explain within the framework of current models. One theory posits the existence of direct collapse black holes, which form from the collapse of massive gas clouds without first going through a star formation phase. These black holes could start with masses of tens of thousands of times the mass of the Sun, giving them a head start in the race to become supermassive. However, the conditions required for direct collapse are rare, involving low metallicity gas and minimal turbulence to prevent fragmentation. Observing evidence of such a process remains a frontier in the study of reionization. The connection between these early black holes and the galaxies that hosted them is another area of intense research. In many cases, the radiation and outflows from actively feeding black holes, known as AGN feedback, can either suppress or enhance star formation in their host galaxies. During the era of reionization, this feedback could have played a dual role, both contributing to the ionization of the universe and shaping the growth of galaxies. The balance between these effects likely depended on factors such as the size of the galaxy and the intensity of the black hole's activity. The role of cosmic feedback extends beyond individual galaxies and black holes. The radiation from the first stars and galaxies interacted with the intergalactic medium, IgM, creating bubbles of ionized gas that gradually expanded and overlapped. This patchy process of reionization was influenced by the clustering of galaxies, with denser regions ionizing more quickly than less populated areas. This non-uniformity in the reionization process has left imprints on the cosmic structure that we can still observe today, such as variations in the large-scale distribution of galaxies and gas. Adding to the complexity of this era is the interplay between different types of feedback mechanisms. In addition to the ionizing radiation from stars, galaxies also produced mechanical feedback in the form of supernova explosions and galactic winds. These processes injected energy into the surrounding gas, influencing its temperature, density, and ability to form new stars. While some feedback effects slowed down star formation by heating or expelling gas, others may have triggered it by compressing gas clouds and promoting collapse. Understanding these opposing effects is crucial for building a complete picture of reionization. Another fascinating aspect of reionization is its potential impact on the cosmic web, the vast, filamentary structure that connects galaxies across the universe. During the Dark Ages, the cosmic web was largely neutral and opaque, but as reionization progressed, it became increasingly ionized and transparent. This transformation not only affected the transmission of light but also the dynamics of the gas within the web. The ionization of the cosmic web likely played a role in regulating the flow of gas into galaxies, influencing their growth and evolution over time. One of the most promising ways to study these large-scale effects is through the 21 cm hydrogen line, a specific wavelength of light emitted by neutral hydrogen atoms. During the Dark Ages and the era of reionization, this signal was abundant, providing a direct probe of the state of the universe's hydrogen gas. By mapping the 21 cm signal across different regions and redshifts, astronomers can trace the progression of reionization and the distribution of matter on cosmic scales. Detecting the 21 cm signal, however, is no easy task. The faintness of the signal, combined with interference from foreground sources like our own galaxy, makes it extremely challenging to observe. Ground-based radio telescopes like LOFAR, Low Frequency Array, and HERA, Hydrogen Epoch of Reionization Array, are working to overcome these challenges, while future space-based missions could provide even more sensitive observations. Success in this area would revolutionize our understanding of reionization, offering a three-dimensional map of this critical period in cosmic history. The importance of studying the era of reionization goes beyond its historical significance. By understanding how the first stars and galaxies formed and evolved, we gain insights into the fundamental processes that govern the universe. These insights have implications for a wide range of topics, from the formation of planetary systems to the nature of dark matter and dark energy. The era also serves as a natural laboratory for testing our theories of physics and cosmology, pushing the boundaries of what we know and challenging us to refine our models. As technology advances, the study of reionization is entering a new golden age. Instruments like the James Webb Space Telescope are poised to provide unprecedented views of the early universe, revealing details about the first galaxies, stars, and black holes. These observations, combined with data from radio telescopes and cosmological simulations, promise to transform our understanding of this pivotal era. Yet, despite these advances, many mysteries remain, from the nature of the first light sources to the exact timeline of reionization and its effects on the universe's structure. The era of reionization stands as one of the most profound chapters in the story of the cosmos. It marks the transition from darkness to light, from simplicity to complexity, and from a universe dominated by fundamental particles to one teeming with galaxies, stars, and planets. It is a testament to the dynamic and ever-changing nature of the cosmos, reminding us that even the darkest epochs are temporary, and that light has the power to transform the universe. The study of the era of reionization continues to open new doors in understanding the mechanisms that sculpted the early universe. One of the most tantalizing puzzles is the exact sequence and timing of events that led to the completion of reionization. By piecing together observational evidence and theoretical models, scientists aim to reconstruct this timeline with increasing precision. The process of reionization is believed to have unfolded in stages. Initially, small pockets of ionized hydrogen, or H2 regions, began to form around the earliest stars and galaxies. These pockets grew in size and number, eventually overlapping to create larger ionized regions. Over time, these regions expanded and merged, gradually transforming the intergalactic medium, IGM, from neutral to ionized. This patchy and nonlinear process likely varied across different parts of the universe, influenced by local variations in the density of matter and the distribution of galaxies. One critical factor in this process is the escape fraction of ionizing photons, the proportion of high-energy photons that managed to escape from their host galaxies into the IGM. For reionization to proceed efficiently, a significant fraction of these photons had to travel beyond their point of origin to ionize surrounding gas. However, the escape fraction depends on various factors, such as the structure of the galaxies, the amount of dust and gas within them, and the energy output of their stars. Simulations suggest that the escape fraction might have varied significantly between galaxies, with smaller, less massive galaxies potentially contributing more to reionization than their larger counterparts. This is because smaller galaxies, with lower gravitational potential, may have had less dense gas around them, allowing more photons to escape. This idea challenges traditional views that focused primarily on massive galaxies and highlights the role of the faintest galaxies in driving cosmic evolution. Adding to the complexity is the potential contribution of exotic sources of radiation. While the first stars and galaxies are widely regarded as the primary drivers of reionization, other sources, such as population 3 stars, could have played a significant role. These stars, made almost entirely of hydrogen and helium, were much hotter and more massive than stars that formed later in cosmic history. Their intense ultraviolet radiation would have been highly effective in ionizing hydrogen, but their short lifespans mean they likely contributed only during the earliest stages of reionization. Another intriguing possibility involves dark matter annihilation or decay. Some theories suggest that certain types of dark matter particles could have emitted radiation as they interacted or decayed. If this occurred, it could have contributed to the ionization of the IGM, especially in regions where dark matter was most concentrated. While speculative, this idea demonstrates the interconnectedness of different cosmic phenomena and highlights the potential for reionization studies to shed light on the nature of dark matter. The interplay between reionization and the large-scale structure of the universe is another area of active research. During the Dark Ages, the distribution of matter was relatively uniform, with small fluctuations in density that eventually grew into the cosmic web of galaxies and clusters we see today. As reionization progressed, it likely influenced the dynamics of this structure by altering the properties of the gas within it. For example, the heating of the IGM during reionization could have suppressed the formation of small galaxies in certain regions, a phenomenon known as photoionization feedback. By preventing gas from cooling and condensing, this feedback would have limited the growth of new galaxies, particularly in low-density regions. This effect may have contributed to the uneven distribution of galaxies across the universe, leaving an imprint on the large-scale structure that can still be observed today. The interplay between reionization and galaxy formation is further complicated by the role of magnetic fields. Although the origin of cosmic magnetic fields remains a mystery, they are thought to have influenced the behavior of gas during the reionization era. By affecting the movement of charged particles, magnetic fields could have shaped the flow of gas into galaxies, altering the rates of star formation and the escape of ionizing photons. Understanding these effects requires a combination of observations and sophisticated simulations that account for the complex physics of magnetized plasmas. One of the most exciting aspects of reionization research is the potential to uncover new physics. The conditions of the early universe were vastly different from those of today, providing a unique environment for testing theories of fundamental forces and particles. For instance, the interactions between ionized gas and radiation during reionization could reveal subtle effects of gravity, electromagnetism, and even quantum mechanics that are difficult to observe in other contexts. At the same time, the study of reionization offers a window into the origins of chemical elements. The first stars, through their nuclear fusion processes, produced heavier elements such as carbon, oxygen, and nitrogen. When these stars ended their lives in supernova explosions, they enriched the surrounding gas with these elements, setting the stage for the formation of later generations of stars and planets. By analyzing the chemical composition of ancient stars and gas clouds, scientists can trace the flow of elements through the universe and gain insights into the early stages of cosmic chemical evolution. The reionization era also has profound implications for the search for life beyond Earth. The conditions established during this period influenced the environments of later star systems, including the formation of planets, and the availability of elements essential for life. By studying reionization, we can better understand the factors that determine the habitability of planets and the likelihood of finding life elsewhere in the universe. Despite the progress made in recent years, the era of reionization remains one of the most enigmatic chapters in cosmic history. Many questions remain unanswered, from the properties of the first stars and galaxies to the details of the reionization process itself. As new telescopes and technologies come online, such as the Square Kilometre Array, (SK), and future space observatories, the potential for groundbreaking discoveries continues to grow. The pursuit of these mysteries is not just about satisfying scientific curiosity. It is a testament to humanity's enduring quest to understand our origins and our place in the universe. The era of reionization, as the dawn of light and structure in the cosmos, represents a turning point in this story, a moment when the universe transitioned from simplicity to complexity, setting the stage for everything that followed. The quest to fully understand the era of reionization is intrinsically tied to the evolution of the universe itself, as every star, galaxy, and cosmic structure owes its existence to the conditions established during this transformative epoch. To unravel its secrets, astronomers employ a diverse array of observational techniques, theoretical models, and simulations, each offering unique insights into this pivotal period in cosmic history. One of the most direct ways to study reionization is through the observation of the cosmic microwave background, CMB. As the afterglow of the Big Bang, the CMB contains subtle imprints of the processes that occurred during the early universe. In particular, the reionization of the intergalactic medium scattered photons of the CMB, leaving a detectable signal known as the Thomson scattering imprint. By analyzing the polarization and temperature fluctuations in the CMB, scientists can estimate the timing and extent of reionization, providing critical constraints on theoretical models. Another crucial observational tool is the study of high-redshift galaxies and quasars, which serve as beacons of light from the early universe. The light emitted by these objects travels through the intergalactic medium on its way to Earth, encountering regions of neutral and ionized gas along the way. By examining the absorption features in their spectra, astronomers can map the distribution of neutral hydrogen and gain insights into the state of the IgM during reionization. One of the most striking features observed in the spectra of distant quasars is the Gunn-Peterson trough, a region of nearly complete absorption caused by the presence of neutral hydrogen. The detection of such troughs in quasars at redshifts greater than 6 suggests that significant portions of the IgM were still neutral during the later stages of reionization. By studying the progression of these features across multiple quasars, researchers can trace the evolution of the IgM and determine when reionization was completed. Complementing these observations are deep field surveys conducted by space telescopes like the Hubble Space Telescope and the James Webb Space Telescope, JWST. These surveys focus on identifying and characterizing galaxies at the highest possible redshifts, pushing the boundaries of our understanding of the early universe. By measuring the properties of these galaxies, such as their luminosity, size, and star formation rates, scientists can infer their contributions to reionization and explore the diversity of structures that existed during this era. One particularly intriguing discovery is the existence of surprisingly faint and small galaxies at redshifts greater than 7. These galaxies, which are often too dim to be detected by ground-based telescopes, are believed to have played a significant role in driving reionization. Their abundance and efficiency in producing ionizing photons suggest that they may have outshone larger, more luminous galaxies in their impact on the IgM. Another groundbreaking observational approach involves the detection of Lyman alpha emission lines, which are produced by hydrogen gas ionized by young, hot stars. These lines provide a direct probe of the ionization state of the surrounding gas, and can reveal the presence of ionized bubbles within the neutral IgM. However, the detection of Lyman alpha lines becomes increasingly challenging at higher redshifts, as the neutral hydrogen in the IgM absorbs much of the emitted light. By studying the distribution and strength of Lyman alpha emission, astronomers can piece together the patchwork of ionized regions that characterize the early universe. In addition to optical and near-infrared observations, radio astronomy offers a powerful window into the era of reionization. One of the most exciting prospects in this field is the detection of the 21 cm line of neutral hydrogen, which provides a direct tracer of the IgM during the dark ages and reionization. This signal, produced by the hyperfine transition of neutral hydrogen atoms, carries information about the temperature, density, and ionization state of the gas. By mapping the 21 cm signal across different redshifts, researchers aim to create a three-dimensional picture of the reionization process. Current and upcoming radio observatories, such as the Low Frequency Array, LOFAR, the Murchison Wide Field Array, MWA, and the Square Kilometer Array, SKA, are at the forefront of this effort. These facilities are designed to detect the faint 21 cm signals from the early universe, overcoming significant challenges such as contamination from foreground sources and the weakness of the signal itself. If successful, these observations could revolutionize our understanding of reionization and provide unprecedented insights into the properties of the first stars and galaxies. Theoretical models and simulations also play a crucial role in interpreting observational data and exploring scenarios that cannot yet be observed directly. Using supercomputers, scientists simulate the evolution of the universe from the dark ages to the end of reionization, incorporating the effects of gravity, radiation, and gas dynamics. These simulations allow researchers to test different hypotheses about the sources of ionizing photons, the escape fraction of radiation, and the role of feedback processes in shaping the IgM. One key advantage of simulations is their ability to explore the interplay between small-scale processes, such as the formation of individual stars and galaxies, and large-scale phenomena, such as the growth of the cosmic web. By bridging these scales, simulations provide a comprehensive view of how the universe transitioned from a neutral, homogeneous state to the complex, ionized structures we observe today. Despite these advances, significant gaps in our understanding remain. For example, the exact properties of the first stars, or population 3 stars, are still largely speculative. These stars are thought to have been massive, luminous, and short-lived, producing copious amounts of ionizing radiation. However, their formation and evolution depend on a delicate balance of factors, including the cooling of primordial gas, the influence of dark matter, and the feedback effects of radiation and supernova explosions. Another unresolved question is the role of black holes in reionization. While star-forming galaxies are widely regarded as the primary drivers, the intense radiation emitted by accreting black holes in the form of quasars and active galactic nuclei could have contributed significantly, especially in regions near these massive objects. Understanding the relative contributions of stars and black holes requires a detailed analysis of their radiation spectra and the spatial distribution of ionized regions. As our observational and theoretical tools continue to improve, the study of the era of reionization is poised to enter a new era of discovery. Each new piece of evidence adds to the intricate tapestry of cosmic history, bringing us closer to answering some of the most profound questions about the origins of light, structure, and complexity in the universe. As the study of the era of reionization continues to evolve, a key challenge remains: the resolution of the sources that provided the energy necessary to ionize the hydrogen gas. While early models focused primarily on stars, it has become increasingly clear that the answer lies in a combination of different cosmic phenomena. The first stars, or population 3 stars, are believed to have been the initial sources of ionizing radiation, but they were not alone. The emergence of active galactic nuclei, AGN, powered by supermassive black holes at the centers of the first galaxies, might have also contributed significantly to the process of reionization. What makes this period particularly intriguing is that it represents a time when the universe was far less uniform than it is today. The cosmic web, the large-scale structure of the universe, was beginning to take shape, with dense clusters of galaxies interconnected by vast voids of empty space. This web-like structure had a profound impact on the reionization process. Ionizing radiation from stars and black holes could travel freely through the low-density regions, but when it encountered the dense filaments of the cosmic web, it was often absorbed, leading to the formation of ionized bubbles within the neutral hydrogen gas. These bubbles gradually grew in size over time, eventually merging and leading to the complete ionization of the IgM. The process of reionization itself, however, was not a uniform event. It occurred in stages. Early models suggested that it was a smooth, global event, but more recent observations indicate that it was highly patchy. Ionized regions formed in bubbles around the sources of ionizing radiation, expanding and merging over time. These regions were likely surrounded by neutral hydrogen gas, which served as a barrier to further ionization. The patches of ionized gas left a distinctive signature in the cosmic microwave background radiation, which scientists can study to better understand how reionization unfolded. These inhomogeneous bubbles provide a clearer picture of the complex interplay between the radiation from the first stars, galaxies, and black holes, and the dense hydrogen gas that filled the universe. Understanding the feedback mechanisms at play during this epoch is also a critical part of the puzzle. The formation of the first stars and galaxies didn't happen in isolation. As they formed, their radiation had an immediate and profound impact on their surroundings. The radiation from these first stars could have heated the surrounding gas, affecting subsequent star formation and potentially slowing or even halting the process of ionization in certain regions. This feedback effect would have influenced the rate at which galaxies and stars could continue to form, potentially leading to star formation suppression in certain parts of the universe. Additionally, supernova explosions, which marked the deaths of the first stars, could have triggered additional processes that further reshaped the intergalactic medium, making it even more complex to model. In terms of galaxy formation, this epoch saw the formation of some of the earliest and most primitive galaxies. The light emitted from these first galaxies played a key role in providing the necessary radiation to ionize hydrogen. However, the nature of these galaxies is still somewhat mysterious. Due to their distance from us and the vast time that has passed since their formation, much of their light is redshifted and difficult to detect. Astronomers rely on both the direct observation of distant galaxies and indirect methods, like the Lyman alpha forest, a collection of absorption lines from neutral hydrogen in the spectra of distant quasars, to learn more about their properties. These observations suggest that the early galaxies were smaller, dimmer, and possibly more chaotic than the galaxies we see today. At the same time, the role of massive black holes cannot be underestimated. In some models, the radiation from the accretion disks of these black holes could have been a dominant source of the high-energy photons needed for reionization. The quasars powered by supermassive black holes at the centers of these early galaxies would have emitted copious amounts of ultraviolet radiation, contributing significantly to the ionization of hydrogen. In fact, it's possible that the intense radiation from quasars could have accelerated reionization in specific regions, potentially acting as the final push in the universe's transition from the dark ages to the fully ionized state we observe today. However, there is still considerable debate about the relative contributions of galaxies versus black holes in the process. In addition to the sources of ionizing radiation, astronomers also focus on the environmental factors that could have influenced reionization. For example, the presence of dark matter might have played a crucial role in shaping the formation of early structures. Dark matter, which interacts only gravitationally with normal matter, could have acted as the scaffolding upon which the first galaxies and stars were built. The gravitational pull of dark matter would have led to the collapse of gas clouds, forming the first stars. The precise nature of the connection between dark matter and the sources of reionization remains one of the many open questions in the field. The role of cosmic winds and outflows. A particularly exciting aspect of reionization involves the study of cosmic winds and outflows. As the first stars and galaxies began to form, they not only emitted radiation but also expelled matter. Supernovae, as well as the energetic feedback from the formation of supermassive black holes, triggered winds that could carry hot gas out of the galaxies, potentially enriching the intergalactic medium with heavier elements and changing the overall structure of the universe. These outflows could have contributed to the metallicity of the early universe, enriching the intergalactic medium with elements necessary for the formation of later generations of stars and planets. Simulations suggest that these galactic outflows may have been far more efficient in the early universe than in later epochs, where more complex feedback processes, such as galactic mergers and the effects of the cosmic microwave background radiation, began to shape the flow of gas. Understanding these outflows not only provides insight into the formation of the early universe but also into how later structures, such as modern galaxies, came to be. The end of the era of reionization. As we approach the end of reionization, the universe entered an era of significant transformation. The process of recombination, when electrons and protons combined to form neutral hydrogen, left a lasting imprint on the cosmos. The end of reionization marks the point when the universe had fully transitioned from a state of darkness and opacity to a transparent, ionized medium, one in which the light from stars could travel freely across vast expanses of space. By the time the universe reached a redshift of around 6, most of the IgM had been reionized, but the legacy of the Dark Ages still lingers. The light emitted during this epoch has been stretched to longer wavelengths over the billions of years that followed, making it difficult to detect directly. However, advances in observational technology, particularly with the development of the James Webb Space Telescope, JWST, are poised to offer new opportunities for studying the earliest galaxies and probing the final stages of reionization in unprecedented detail. The JWST, with its infrared capabilities, promises to revolutionize our understanding of the era of reionization by allowing scientists to peer deeper into the universe's past than ever before. Its ability to observe the faintest, most distant galaxies will provide new insights into the conditions that existed during this transformative period, helping to answer lingering questions about the sources of ionizing radiation, the role of supermassive black holes, and the intricate feedback mechanisms that shape the evolution of the universe. The era of reionization stands as one of the most critical junctures in cosmic history, marking the transition from a featureless, dark, and neutral universe to one filled with light, structure, and the potential for complexity. It is a period in which the fundamental forces that shape the universe, gravity, radiation, and matter, interacted in a delicate and fascinating dance, setting the stage for everything that came after. Understanding this epoch is essential not only for uncovering the origins of our own cosmic neighborhood but also for answering the larger questions about the nature of the universe and its ultimate destiny. As we continue to dive into the mysteries of the era of reionization, it's important to reflect on how this period influences our understanding of the universe today. The processes that unfolded during this time helped to establish the basic structure of the universe as we see it. Without the energy provided by the first stars, galaxies, and black holes, the universe would have remained a dark, featureless expanse, devoid of the luminous objects that fill it now. The radiation that flooded the universe during reionization provided the foundation for the formation of the galaxies, clusters, and larger cosmic structures that we observe today. One of the most fascinating aspects of the era of reionization is its connection to the observable universe. Even though it occurred billions of years ago, the legacy of reionization is still etched into the fabric of the cosmos. For example, the cosmic microwave background (CMB), which serves as a snapshot of the universe when it was just 380,000 years old, provides valuable clues about the early universe. While the CMB itself predates reionization, it carries subtle imprints from the event, especially in the form of temperature fluctuations. These fluctuations give astronomers insight into how the universe transitioned from a neutral state to one filled with ionized gas, and they are key to understanding the timeline of reionization. In addition, the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars, offers indirect evidence of reionization. These absorption lines, caused by neutral hydrogen, provide a glimpse of the state of the intergalactic medium before it was fully ionized. By studying how these absorption lines evolve over time, scientists can map the progression of reionization and gain insights into the sources that powered this transformative epoch. The era of reionization also influences our understanding of galaxy evolution. The first galaxies formed during this period were unlike anything we see today. They were smaller, less stable, and far more chaotic. The radiation from these galaxies not only ionized the surrounding gas but also affected their own star formation processes. Understanding how these early galaxies evolved during reionization helps astronomers build models of galaxy formation and evolution that can explain how the complex, large-scale structures of the universe came to be. The feedback mechanisms that operated during reionization also shaped the future of galaxy formation. The intense radiation from the first stars and black holes heated and ionized the surrounding gas, preventing it from collapsing to form new stars in certain regions. At the same time, outflows from supernovae and active galactic nuclei pushed gas out of galaxies, enriching the intergalactic medium with heavier elements and altering the structure of the universe. These processes, which are still active in galaxies today, played a crucial role in determining the size, composition, and evolution of galaxies throughout cosmic history. The feedback loops from these early processes continue to resonate in the modern universe. For instance, the presence of supermassive black holes at the centers of most galaxies today is a direct result of the cosmic conditions set by reionization. As galaxies merged and grew larger, black holes formed at their centers, feeding off the surrounding gas and eventually becoming powerful engines capable of emitting vast amounts of radiation. This radiation not only powered the growth of these black holes but also influenced the evolution of the galaxies that host them, continuing the cycle of cosmic feedback that began during reionization. Today, astronomers are working on sophisticated simulations that model the era of reionization. These simulations use data from the cosmic microwave background, observations of distant galaxies, and quasar spectra to create virtual universes that resemble our own. By tweaking the parameters of these models, such as the rate of star formation, the strength of black hole feedback, and the properties of the intergalactic medium, scientists can test different theories about how reionization unfolded. These simulations are crucial for understanding the precise mechanisms that governed this epoch and for interpreting the data gathered by observatories like the James Webb Space Telescope, JWST. The JWST, with its advanced infrared capabilities, is expected to provide a wealth of new data on the era of reionization. Unlike previous telescopes, which were limited by the amount of light they could detect, the JWST is designed to peer deeper into the universe's past, looking at galaxies that formed just a few 100 million years after the Big Bang. Its ability to observe the faintest and most distant galaxies will allow astronomers to study the early stages of galaxy formation and the impact of reionization on the surrounding gas. With the help of the JWST, astronomers hope to answer some of the most pressing questions about the era of reionization, such as the identity of the first stars and galaxies and the relative contributions of different sources of ionizing radiation. The telescope's ability to observe distant galaxies in unprecedented detail will allow scientists to directly observe the sources that powered reionization and gain new insights into the processes that shaped the early universe. Furthermore, as the technology improves, we may be able to push our understanding even further back in time, potentially observing the first light, the moment when the first stars began to shine. This moment is considered by many to be one of the most important events in cosmic history, as it marks the transition from a dark, featureless universe to one filled with light, structure, and the potential for complexity. By studying the light from these first stars, we may be able to learn more about the physics of the early universe and the processes that led to the formation of the first galaxies. In many ways, the era of reionization is still a frontier in cosmology. Despite the tremendous advances we've made in our understanding of this period, many mysteries remain unsolved. How exactly did the first stars form? What role did black holes play in the ionization of the universe? How did the feedback from early galaxies shape the structure of the universe? These are just a few of the questions that astronomers continue to explore, and with each new discovery, we come closer to unraveling the secrets of the dawn of light in the universe. The era of reionization represents one of the most transformative periods in cosmic history. It was a time when the universe was forever changed by the birth of stars, galaxies, and black holes, shaping the structure of the cosmos and setting the stage for everything that came afterward. Our understanding of this epoch is still in its infancy, But with new observations and advanced simulations, we are inching closer to unlocking the mysteries of this fascinating period. The dawn of light in the universe may have occurred billions of years ago, but its echoes continue to resonate throughout the cosmos, shaping the universe we observe today. As we continue exploring the era of reionization, it's crucial to delve deeper into the scientific techniques and observational breakthroughs that are shaping our understanding of this pivotal period in cosmic history. One of the most groundbreaking tools in this research has been the cosmic microwave background (CMB) radiation, which, though originating long before reionization, carries vital clues about the state of the universe during the reionization process itself. The CMB is often described as the afterglow of the Big Bang, providing a snapshot of the universe when it was only about 380,000 years old. This radiation, which fills the entire sky, has been studied intensively to measure temperature fluctuations that arose from density differences in the early universe. These fluctuations, while mainly influenced by conditions before reionization, also hold crucial information about the transition from a neutral to an ionized state. Through these fluctuations, scientists have learned that the intergalactic medium, IGM, during reionization was not uniform, with some areas being more ionized than others, creating a patchwork pattern in the early universe that is detectable through these CMB fluctuations. However, the CMB alone does not provide direct observations of the reionization process. To address this, astronomers turn to quasars and the Lyman alpha forest. Quasars, the intensely bright centers of distant galaxies, are powered by supermassive black holes. As light from these quasars travels across the universe, it interacts with hydrogen atoms, leaving an imprint on the light's spectrum. The Lyman alpha forest refers to the series of absorption lines that appear in the spectra of distant quasars, caused by the presence of neutral hydrogen in the IGM. The amount and distribution of neutral hydrogen give astronomers insight into the state of reionization. By studying how these absorption lines evolve with redshift, researchers can track how the universe transitioned from a neutral to an ionized state, offering a timeline for the era of reionization. In the 21st century, the most powerful tool for investigating this period has been the James Webb Space Telescope, JWST, which is uniquely equipped to observe the faintest and most distant galaxies. The JWST's infrared capabilities allow it to look further back in time than any previous observatory, offering unprecedented views of the earliest stars and galaxies. By observing distant galaxies that formed just a few 100 million years after the Big Bang, the JWST promises to offer new insights into the sources that powered reionization. One of the key questions the JWST aims to answer is the nature of the first galaxies. Scientists believe these galaxies were much smaller than the ones we see today, and they likely formed from the collapse of gas clouds that were largely composed of hydrogen and helium. However, understanding exactly how these galaxies formed and evolved during reionization is a significant challenge. Did they form in isolation, or were they part of larger structures? What role did supermassive black holes play in their evolution? The answers to these questions will reshape our understanding of galaxy formation and evolution. The exact sources of ionizing radiation that triggered reionization remain one of the biggest mysteries of this epoch. While it is clear that the first stars, known as population 3 stars, played a crucial role, there is still much we don't know about their properties. These stars were likely much more massive than those we see today, burning hotter and faster, which could have led to a rapid release of ultraviolet radiation. But were population 3 stars the only contributors to reionization? Recent studies suggest that the first galaxies, as well as black holes, may have also played an important role in reionizing the universe. The first supermassive black holes, which were already present in the early universe, could have emitted vast amounts of radiation, further accelerating the reionization process. Another potential contributor to reionization is X-ray radiation. Recent theories suggest that X-rays, which are more energetic than ultraviolet light, might have been responsible for ionizing the hydrogen in the IGM. If this theory proves correct, it would challenge the traditional view that ultraviolet radiation from stars and galaxies was the dominant driver of reionization. By studying the X-ray emissions from distant galaxies and black holes, astronomers are beginning to probe this possibility. In addition to the radiation sources, we must also consider the cosmic structure that formed during this time. The process of reionization was not uniform. Some regions of the universe became ionized much earlier than others, creating an uneven distribution of ionized and neutral gas. This patchy ionization played a critical role in shaping the large-scale structure of the universe. As the first stars and galaxies began to ionize their surroundings, they created bubbles of ionized gas that gradually expanded and merged. These bubbles eventually filled the universe with ionized hydrogen, but the process was far from uniform. Some areas of the universe remained neutral for longer periods, while others became ionized much sooner, creating a complex and varied landscape in the early universe. This uneven distribution of ionization is still observable today. In fact, it's possible to see remnants of the era of reionization in the structure of the universe around us. The large-scale cosmic web, the vast network of galaxies and gas that fills the universe, is thought to have formed as a result of the reionization process. As gas was ionized, it lost its ability to collapse into dense clouds, preventing the formation of new stars in certain regions. This, in turn, contributed to the formation of galaxy clusters, voids, and filaments that we observe in the modern universe. The study of the intergalactic medium, IGM, is also crucial in understanding reionization. During the era of reionization, the IGM transitioned from being almost entirely neutral to being mostly ionized. This shift had profound implications for the formation of galaxies and the propagation of light throughout the universe. Neutral hydrogen absorbs ultraviolet light, but once the gas becomes ionized, it allows light to travel more freely, enabling the first galaxies to shine through the fog. The reionization process also affected the evolution of the IGM itself. As the universe expanded, the IGM cooled, and the density of hydrogen gas decreased. This cooling allowed the formation of the first galaxies, which in turn emitted radiation that further ionized the surrounding gas. To fully understand the intricacies of this process, astronomers are using cosmological simulations to model the events of reionization. These simulations take into account factors such as star formation, black hole growth, and the behavior of the IGM, among other variables, to create a virtual universe that mirrors the one we observe today. By comparing the results of these simulations with observational data from the CMB, Quasars, and the JWST, scientists can refine their models of reionization and gain a clearer picture of how the universe evolved during this critical period. One of the challenges in studying reionization is that the events of this period are not directly observable. The radiation that filled the universe during reionization is not detectable by traditional telescopes, and the objects that produce this radiation are often too faint to observe directly. Instead, scientists rely on indirect evidence, such as the effects of reionization on the CMB and the spectra of distant quasars, to piece together the story of this era. The era of reionization is not just a fascinating chapter in the history of the universe. It is also a crucial puzzle piece in the broader picture of cosmic evolution. Understanding how the universe went from a dark, featureless expanse to the vibrant, complex cosmos we see today is key to understanding the origins of galaxies, stars, and planets. And as technology continues to advance, with tools like the JWST, we are poised to unlock even more secrets of this enigmatic era, bringing us one step closer to understanding the birth of light in the universe. As we continue, we dive deeper into the larger implications of understanding the era of reionization, especially as it pertains to the search for life elsewhere in the universe. The formation of the first stars, galaxies, and the overall structure of the universe not only shaped the cosmic landscape but also created the necessary conditions for life as we know it. The transition from the cosmic dark ages to the first moments of illumination is a key turning point, one that holds significant promise for astrobiology and the search for extraterrestrial life. The era of reionization marks the point at which the universe became transparent to light, which paved the way for the formation of complex structures like galaxies and, eventually, planets. Before this period, the universe was essentially a dark, dense fog of neutral hydrogen gas. light from stars and other radiation sources had little chance of penetrating this fog, making it difficult for galaxies to form in any meaningful way. However, as reionization progressed, the universe began to clear up, allowing light to travel freely across vast distances. This transparency is critical for the study of distant exoplanets in our own time. Understanding how the universe transitioned from opaque to transparent has profound implications for how we search for habitable planets. Astronomers are able to observe distant exoplanets through the light that they emit or reflect, and studying the interaction between light and these planets can reveal key details about their atmosphere, surface conditions, and potential for life. But it all traces back to that pivotal moment when the universe became clear enough to allow light to travel through it, carrying with it the information we need to search for life. This relationship between reionization and the potential for life is further explored by the study of how the first galaxies contributed to the conditions necessary for life. The formation of stars and galaxies during the era of reionization wasn't just about lighting up the universe. It was about setting the stage for chemical processes that would eventually lead to the creation of the elements necessary for life. Elements such as carbon, oxygen, nitrogen, and others, essential to life as we understand it, were forged inside the cores of the first stars. These elements were then released into the cosmos during the process of supernova explosions, seeding the universe with the building blocks of life. This realization ties directly into the search for extraterrestrial life. The very same processes that led to the formation of stars and galaxies in the early universe also created the possibility for planets that could support life. The study of distant galaxies and the remnants of the first stars can help us understand the conditions necessary for life to arise, not just on Earth, but throughout the cosmos. By examining how other galaxies and star systems formed during reionization, scientists can begin to understand the potential for life in the vast expanse of the universe. In this regard, the James Webb Space Telescope, JWST, plays a critical role in our efforts to probe the very edges of the universe, where the first galaxies formed. By looking back to the early universe, the JWST allows astronomers to detect galaxies that are up to 13 billion light-years away. These galaxies are so distant that their light has taken nearly the entire history of the universe to reach us, offering a glimpse into the universe at the moment when reionization was underway. The data provided by the JWST will be instrumental in understanding how these early galaxies formed, how they contributed to the reionization process, and how they may have set the stage for the emergence of habitable worlds. Additionally, by analyzing the spectra of distant galaxies, scientists can identify the chemical signatures of the first stars and the gases that surrounded them. These signatures can reveal the conditions under which these early galaxies formed and evolved, offering critical insights into the processes that created the first habitable environments. Understanding these processes can provide valuable clues about the potential for life elsewhere in the universe, as the conditions that fostered life on Earth may not be unique to our planet but could exist in other parts of the cosmos as well. As we continue to investigate the era of reionization, it's essential to understand the cosmic timeline of this period. Reionization didn't occur all at once. It was a gradual process that took place over several 100 million years. The timeline of reionization can be divided into three main phases: the early reionization phase, the peak reionization phase, and the late reionization phase. In the early phase, the first stars and galaxies began to form and emit ultraviolet radiation. This radiation was initially absorbed by the surrounding hydrogen gas, ionizing it in small pockets. These ionized regions, or bubbles, expanded over time as more stars and galaxies formed, but much of the universe remained opaque and neutral during this phase. The first galaxies, though small and dim, played a crucial role in this early phase by producing the radiation necessary to begin reionization. As we move into the peak reionization phase, which occurred roughly between 10 and 13 billion years ago, the universe began to experience more widespread ionization. Larger galaxies and clusters of galaxies formed during this period, emitting more powerful bursts of radiation that ionized the surrounding hydrogen. During this phase, the bubbles of ionized gas began to merge, and large regions of the universe became fully ionized. This period marked the most intense phase of reionization, as the universe transitioned from being mostly neutral to mostly ionized. The final stage, the late reionization phase, occurred around 11 billion years ago and continued until about 13 billion years ago. By this point, reionization was almost complete, and the universe had reached the state we observe today, where most of the hydrogen is in an ionized state, and light can travel freely through space. The late phase of reionization also coincided with the formation of more complex structures like galaxy clusters and large-scale cosmic filaments. This timeline is essential for understanding how the universe evolved and how different regions of the universe underwent reionization at different rates. This patchy process of ionization left a lasting imprint on the structure of the universe, influencing how galaxies and large-scale structures continue to evolve to this day. The study of reionization is, therefore, not just about understanding the past, but also about understanding the future evolution of the cosmos. Moreover, the study of reionization provides crucial insights into the physical processes that govern the evolution of galaxies. By observing distant galaxies in the early stages of reionization, scientists can learn about how galaxies form, grow, and interact with their surroundings. These insights are essential for understanding how galaxies evolve over time, from their earliest stages to their current state. The era of reionization is a defining moment in the history of the universe. It marks the transition from a dark, featureless expanse to a universe filled with light, energy, and the building blocks for life. By studying this epoch, we not only learn about the formation of the first stars and galaxies but also uncover the fundamental processes that shape the universe as we know it. From understanding the physics of ionization to examining the role of the first galaxies in creating the conditions for life, the era of reionization holds the key to many of the most profound questions about the cosmos, our place in it, and the possibility of life beyond our planet. As we continue to explore the era of reionization, it's important to also address how this period ties into the larger cosmic narrative. It's often said that studying the universe's past is like peeling back layers of an onion. Each layer reveals something about the forces and events that led to our present state. The era of reionization is one of the deepest, most revealing layers of this cosmic onion, offering insights into the fundamental forces that have shaped not only galaxies, but also the very fabric of space-time. When we think about the impact of reionization on the evolution of the universe, we cannot ignore the role of cosmic feedback mechanisms. These mechanisms describe the intricate ways in which the first stars and galaxies influenced their environments. Feedback refers to the interaction between different components of the universe, such as stars, gas, and dark matter, and how these interactions shape the evolution of the cosmos. During reionization, the first stars didn't just illuminate the universe. They also heated and ionized the surrounding gas, a process that had far-reaching consequences. One of the most significant feedback processes involved the heating of the intergalactic medium, IgM. The IgM is the vast, diffuse gas that exists between galaxies. Before reionization, this gas was cold and neutral, but the radiation from the first stars began to heat it. This increase in temperature affected the overall dynamics of galaxy formation. The hotter IgM meant that gas within galaxies could collapse more easily, leading to the creation of new stars. However, this process wasn't uniform. Some regions of the IgM were heated more than others, leading to a patchy and uneven reionization. The feedback between galaxies and the IgM was not just a one-way street. The radiation from galaxies affected the gas, and the gas, in turn, influenced the formation of new galaxies. These cosmic feedback loops are essential to understanding the complexities of galaxy formation during the early universe. The first galaxies, and the stars within them, were the engines driving this feedback. The radiation they emitted not only ionized the hydrogen but also enriched the surrounding gas with heavier elements like carbon, oxygen, and nitrogen. This enrichment process would ultimately lead to the formation of planets, stars, and galaxies that we observe today. However, this process didn't happen uniformly across the universe. There were large regions that remained unaffected by reionization for a time, forming cosmic voids, where no galaxies existed. The study of these voids can provide us with insights into how matter and radiation interacted during reionization, and how the structure of the universe evolved over time. As we look deeper into the epoch of reionization, we also confront some of the most challenging questions about the nature of the first stars and galaxies. For a long time, astronomers believed that the first stars, known as population 3 stars, were made solely of hydrogen and helium, the only elements that existed after the Big Bang. These stars were thought to be massive, short-lived, and incredibly hot, burning through their fuel at an astonishing rate. It was believed that they exploded in supernovae, seeding the universe with heavier elements like carbon, oxygen, and iron, elements crucial to the formation of planets and life. However, recent discoveries and simulations have called this simple narrative into question. While population 3 stars undoubtedly played a significant role in reionization, newer research suggests that the formation of the first galaxies may have been more complex than originally thought. It's possible that some of the first galaxies formed from smaller, less massive stars, possibly even stars that were born from slightly heavier elements than previously believed. These stars would have had a different effect on their environment, altering the way in which reionization unfolded across the universe. As we piece together the nature of the first galaxies, we also need to consider the role of dark matter. Dark matter, which is invisible and undetectable by conventional means, makes up about 27% of the universe's mass energy content. While it doesn't emit light or interact with regular matter in any direct way, dark matter plays a crucial role in the formation of large-scale structures. In the context of reionization, dark matter likely helped seed the formation of the first galaxies. By providing the gravitational pull necessary to draw in ordinary matter, dark matter acted as a sort of scaffolding for the creation of the first cosmic structures. Dark matter's role in the era of reionization is also deeply connected to its mysterious nature. Despite decades of study, scientists still don't know exactly what dark matter is. Various theories abound, ranging from exotic particles like WIMPs, weakly interacting massive particles, to more speculative ideas like axions or sterile neutrinos. What we do know is that dark matter exerts a gravitational influence, and that influence was critical in shaping the formation of galaxies during reionization. Understanding dark matter could, therefore, provide us with not only answers about the universe's earliest epochs but also clues about the most fundamental components of the universe itself. As we shift from the large-scale structure of the universe to the individual components, it's important to discuss the observational techniques that have made studying the era of reionization possible. For years, astronomers relied on ground-based telescopes and space telescopes like Hubble to study distant galaxies and stars. However, studying reionization required looking farther back in time, to the very early universe. That's where the James Webb Space Telescope, JWST, comes in. The JWST, with its cutting-edge infrared capabilities, is designed to look deeper into the universe than ever before, reaching back to the first few 100 million years after the Big Bang. The JWST's ability to detect faint infrared signals from the earliest galaxies is revolutionary. These signals come from the first stars and galaxies, whose light has been stretched and redshifted as the universe has expanded. By studying these redshifted signals, astronomers can gain insights into the timing and progression of reionization. Furthermore, the JWST's spectroscopic capabilities allow scientists to directly study the composition of distant galaxies and star-forming regions, providing crucial information about the chemical processes that occurred during reionization. The JWST isn't the only tool at our disposal. Other observatories, such as the Atacama Large Millimeter Array, ALMA, in Chile, are also critical in the study of reionization. ALMA, with its array of radio telescopes, allows scientists to study the cold gas in distant galaxies, helping to fill in the gaps about how the intergalactic medium evolved during reionization. Observatories like Herschel and the Planck satellite have also contributed to our understanding of the early universe, using different wavelengths to map the cosmic microwave background radiation and study the distribution of matter across the cosmos. As we continue to develop better tools and technology, we will be able to answer many of the questions that remain about reionization. We still don't fully understand the exact mechanisms that led to the ionization of hydrogen gas, the formation of the first galaxies, or the specific characteristics of the first stars. But what we do know is that the era of reionization was a pivotal moment in the history of the universe, one that paved the way for the structures we see today. By studying this period, we not only learn about the past but also gain a deeper understanding of the present and future of the cosmos. Ultimately, the era of reionization is more than just a chapter in the history of the universe. It is a key that unlocks the mysteries of the cosmos. It offers us clues about the origins of the first stars, galaxies, and the fundamental processes that gave rise to the universe as we know it. As we continue to investigate this epoch through cutting-edge technology and innovative research, we inch ever closer to answering some of the most profound questions about the nature of the universe, the origins of life, and the potential for life elsewhere in the cosmos. The era of reionization is a stark reminder of how much there is yet to discover about the universe. While modern astronomy has provided a detailed picture of certain events in cosmic history, reionization remains one of the most enigmatic and fascinating periods. Its study involves a delicate interplay between theory, observation, and simulation, each method offering a different lens to uncover the truths of the early universe. To appreciate the complexity of this era, we need to revisit the nature of hydrogen reionization. When we describe reionization, what we're really talking about is the transformation of hydrogen, the most abundant element in the universe. Initially, after the Big Bang, hydrogen existed in a neutral state. Its protons and electrons were bound together, and as a result, it didn't interact much with the light traveling through the cosmos. This lack of interaction made the universe effectively opaque. But during the era of reionization, the ultraviolet UV radiation emitted by the first stars and galaxies began breaking apart these hydrogen atoms, splitting them into free protons and electrons. This process turned the universe from opaque to transparent, fundamentally changing how light traveled through space. However, hydrogen reionization didn't happen all at once. The universe wasn't bathed in light overnight. Instead, this process occurred in a patchy, uneven manner. As the first stars and galaxies formed, they created ionized bubbles around themselves. These bubbles gradually grew and merged as more sources of UV radiation emerged. Eventually, these ionized regions spread throughout the cosmos, completing the transformation of the universe. But this patchy nature of reionization means that different areas of the universe experienced it at different times. Understanding this patchiness is one of the biggest challenges for astronomers studying this epoch. Another key question about reionization concerns the sources of the UV radiation responsible for it. While we know that the first stars played a significant role, recent studies suggest that galaxies might have contributed more UV light than previously thought. These early galaxies were much smaller and less luminous than the massive galaxies we see today, but their combined radiation could have been enough to ionize large swathes of the universe. Some astronomers even propose that black holes, particularly those at the centers of the first galaxies, might have contributed additional radiation through their accretion disks. These disks, which form as matter spirals into a black hole, can emit enormous amounts of energy, including UV light. Interestingly, studying the sources of reionization also opens up questions about the formation of black holes in the early universe. Did they form from the collapse of massive stars, or did they arise through other processes, such as the direct collapse of gas clouds? These questions are closely tied to the study of reionization because the energy output of early black holes could have influenced the ionization of the surrounding gas. Moreover, understanding the growth of these black holes can shed light on how supermassive black holes, millions or billions of times the mass of our Sun, came to exist relatively early in the universe's history. As we delve deeper into the mechanisms behind reionization, we also encounter the concept of cosmic variance, the idea that different parts of the universe experience slightly different histories. This variance arises from the initial density fluctuations in the universe, which led to the formation of galaxies and clusters in some regions, while other areas remained relatively empty. These differences in density affected the progression of reionization, with denser regions becoming ionized earlier than less dense ones. By mapping these differences, astronomers can gain insights into the distribution of matter in the early universe and the processes that drove its evolution. One of the most exciting aspects of studying the era of reionization is the potential to uncover new types of astrophysical phenomena. For example, some scientists hypothesize the existence of dark stars, theoretical objects powered not by nuclear fusion but by the annihilation of dark matter particles. These stars, if they existed, could have been some of the first luminous objects in the universe, contributing to reionization in ways we don't yet fully understand. While the existence of dark stars remains speculative, their study highlights the innovative approaches scientists are taking to solve the mysteries of the early universe. Another intriguing topic is the role of cosmic magnetic fields during reionization. While we typically think of magnetic fields as relatively minor players in the grand scheme of the universe, they could have influenced the behavior of gas and the formation of stars during this epoch. Some researchers believe that magnetic fields might have been generated during the Big Bang or through the interactions of particles in the early universe. These fields could have shaped the structure of the first galaxies and the dynamics of ionized gas during reionization, adding another layer of complexity to this already intricate period. From a technological perspective, the study of reionization represents one of the most ambitious scientific endeavors of our time. Instruments like the James Webb Space Telescope, the Square Kilometre Array, (SK), and other next-generation observatories are designed to push the boundaries of what we can observe. These telescopes are not only looking for the faintest galaxies and stars but also for the subtle signals of the reionization process itself. For instance, scientists are using 21 cm hydrogen line radiation, a specific type of radio signal emitted by neutral hydrogen, to map the distribution of gas during reionization. By studying these signals, researchers can create a three-dimensional picture of how the universe transitioned from its dark, neutral state to its current ionized form. As these technologies come online, they promise to answer some of the most pressing questions about reionization. How long did it take for the universe to become fully ionized? What were the relative contributions of stars, galaxies, and black holes to this process? And how did the interplay between radiation, matter, and dark matter shape the universe we see today? Each of these questions is a piece of the larger puzzle, and together they form a comprehensive picture of one of the most transformative periods in cosmic history. But perhaps the most profound aspect of studying the era of reionization is what it tells us about our own place in the universe. This epoch represents the dawn of structure, the moment when the universe went from a dark, formless expanse to a vibrant, dynamic cosmos filled with light and life. By understanding this period, we gain not only a deeper appreciation for the forces that shape the universe but also a greater sense of connection to the cosmos. The light that first illuminated the universe billions of years ago is the same light that we now study, a reminder of the enduring legacy of the first stars and galaxies. The legacy of the era of reionization isn't just etched into the light that we observe today, it is also imprinted in the large-scale structure of the universe itself. This period shaped the distribution of galaxies, clusters, and voids that we see when we peer deep into space. The interplay between dark matter, gas, and radiation during reionization created a cosmic web of matter, with dense nodes and filaments surrounded by vast, empty regions. This structure forms the backbone of the universe and serves as a blueprint for all subsequent cosmic evolution. Dark matter, an enigmatic and invisible component of the cosmos, played a crucial role during this era. While it doesn't interact with light or ordinary matter in the way that we might expect, dark matter's gravitational influence was instrumental in the formation of the first galaxies. As neutral hydrogen began to collapse under the influence of gravity, it was dark matter that provided the scaffolding. These halos of dark matter acted as cradles for the first stars and galaxies, concentrating ordinary matter and kickstarting the reionization process. The formation of the first galaxies within these halos is one of the most complex and intriguing phenomena to study. These galaxies were far smaller and less massive than their modern counterparts, but their intense activity makes them fascinating. Unlike the well-ordered spiral and elliptical galaxies we see today, these early galaxies were chaotic and turbulent, driven by rapid star formation and frequent supernovae. These violent processes expelled gas and energy into the surrounding medium, shaping the environment and contributing to reionization. Supernovae, in particular, were pivotal during reionization. When the most massive stars reached the end of their lives, they exploded in spectacular fashion, releasing vast amounts of energy. This energy not only ionized nearby gas but also created shockwaves that compressed surrounding material, potentially triggering the formation of new stars. These cycles of star formation and destruction were critical to the progress of reionization, providing the energy needed to transform the universe while also sowing the seeds for future cosmic structures. But what about the elements that were forged in these first stars? During the era of reionization, the universe transitioned from being composed almost entirely of hydrogen and helium to a place where heavier elements, what astronomers call metals, began to emerge. These metals were created through nuclear fusion in the cores of the first stars and were dispersed into the interstellar medium by supernovae. This process, known as chemical enrichment, marked the beginning of the universe's journey toward complexity. Without it, the building blocks of life, elements like carbon, oxygen, and nitrogen, wouldn't exist. As reionization progressed, it didn't just affect the immediate environment around the first stars and galaxies. It had far-reaching consequences for the entire universe. One of the most significant effects was the heating of intergalactic gas. Before reionization, this gas was cold, dense, and largely neutral. But as UV radiation from early stars and galaxies spread throughout the cosmos, it heated and ionized the gas, making it less dense and more dynamic. This change in the behavior of intergalactic gas had profound implications for the formation of later generations of galaxies, as well as for the overall evolution of the universe. This heating also had an interesting side effect: it suppressed the formation of smaller galaxies. As the gas in the universe became ionized and heated, it was less able to cool and collapse to form new stars, especially in smaller dark matter halos. This suppression of star formation in small galaxies is a key feature of reionization and helps explain why we don't see as many small galaxies today as we might expect. It also underscores the interconnected nature of cosmic evolution, how events during the era of reionization set the stage for everything that came afterward. While the observational evidence for reionization has grown significantly in recent years, many questions remain. For example, the exact timing of reionization is still a topic of active research. Observations of the cosmic microwave background (CMB) suggest that reionization began around 400 million years after the Big Bang and was largely complete by about 1 billion years. However, there is evidence to suggest that reionization may have occurred in fits and starts, with periods of rapid ionization followed by relative lulls. Understanding these fluctuations is key to piecing together the full story of this epoch. To probe these details, astronomers rely on cutting-edge simulations that model the interactions between matter, radiation, and gravity during reionization. These simulations are incredibly complex, requiring supercomputers to process vast amounts of data. They provide insights into the formation of the first galaxies, the growth of ionized bubbles, and the evolution of the intergalactic medium. By comparing these simulations to observations, researchers can test their theories and refine their understanding of the reionization process. One of the most promising observational techniques for studying reionization is the search for Lyman alpha emission, a specific wavelength of light emitted by hydrogen gas. This emission is a powerful tracer of star formation and ionization in the early universe. By observing galaxies that emit Lyman alpha light, astronomers can map the distribution of ionized and neutral gas during reionization. However, this technique is not without challenges. Lyman alpha light can be absorbed by neutral hydrogen, making it difficult to detect in certain regions. Overcoming these challenges requires a combination of advanced instrumentation and clever observational strategies. The future of reionization research is incredibly exciting. With the launch of new telescopes and the development of innovative techniques, we are poised to make groundbreaking discoveries about this epoch. Instruments like the James Webb Space Telescope, JWST, are already revolutionizing our ability to observe the early universe, providing unprecedented views of the first galaxies and their environments. Similarly, radio telescopes like the Square Kilometre Array, SKA, are set to transform our understanding of the intergalactic medium, offering detailed maps of the 21-centimeter hydrogen line that will reveal the structure of the universe during reionization. These advancements also open the door to exploring new and unexpected phenomena. For instance, the detection of gravitational waves from the early universe could provide a unique window into the era of reionization. These ripples in spacetime, caused by massive cosmic events, might carry information about the formation of the first stars and black holes, offering a completely different perspective on this epoch. Ultimately, the era of reionization is more than just a chapter in cosmic history. It is a story of transformation, innovation, and discovery. It is the period when the universe first came alive with light, when the seeds of complexity were sown, and when the framework for everything we see today was established. By studying this epoch, we not only learn about the forces that shape the cosmos but also deepen our connection to the universe and our place within it. As we continue to explore this epoch, we are reminded of how interwoven the universe's history is with its present structure. Each discovery about reionization has far-reaching implications, influencing everything from our understanding of galaxy formation to the distribution of matter across vast cosmic scales. One fascinating aspect of this era is the role of quasars, extraordinarily bright and energetic sources powered by supermassive black holes. These objects, located at the centers of galaxies, emit intense radiation that can ionize gas on a massive scale. Quasars are thought to have been significant contributors to reionization, particularly in their local environments. When these supermassive black holes consumed surrounding material, they released immense energy in the form of ultraviolet and X-ray radiation, creating bubbles of ionized gas. Observing these quasars and their surrounding regions gives astronomers a detailed look at the state of the universe during reionization. However, quasars are not evenly distributed across the universe, and their influence during reionization was likely sporadic and localized. This uneven contribution adds complexity to our models of reionization, as we attempt to understand how such powerful but isolated sources interacted with the broader sea of stars and galaxies that were also driving the process. Additionally, the light from quasars is often absorbed by intervening neutral hydrogen, creating a phenomenon known as the Gunn-Peterson trough. This absorption feature allows astronomers to estimate the amount of neutral hydrogen in the universe at different points in time, providing a crucial piece of the reionization puzzle. But quasars weren't the only exotic phenomena at play during this time. The era of reionization also witnessed the formation of the first black holes. These early black holes, much smaller than the supermassive ones found in quasars, likely formed as remnants of the first massive stars. Known as seed black holes, they could have grown over time through accretion, eventually becoming the behemoths we observe in the centers of galaxies today. The interactions between these early black holes, their host galaxies, and the surrounding medium remain an active area of research, as they offer clues about the origins of some of the universe's most extreme objects. Meanwhile, the interplay between radiation and matter during reionization created a rich tapestry of effects that we can observe today. One such effect is the Sunyaev-Zeldovich effect, where ionized gas interacts with the cosmic microwave background, CMB. This interaction leaves subtle imprints on the CMB that can be detected with sensitive instruments. By studying these imprints, astronomers can learn about the distribution and properties of ionized gas during reionization, shedding light on the processes that shape the universe at this crucial time. Another exciting avenue of research involves gravitational lensing, where massive objects like galaxy clusters bend and magnify the light from distant sources. This effect allows us to peer deeper into the universe than ever before, providing a magnified view of galaxies and structures that formed during reionization. Gravitational lensing has already revealed some of the earliest known galaxies, and future observations promise to uncover even more. As our tools for exploring the universe improve, so too does our ability to simulate the conditions of the era of reionization. High-resolution simulations now allow researchers to model the interactions between stars, galaxies, and the intergalactic medium with incredible detail. These simulations are essential for testing our theories, as they help us understand how different factors, such as the distribution of dark matter, the rate of star formation, and the properties of ionizing radiation, combine to drive reionization. Comparing these models with observations from telescopes like the James Webb Space Telescope helps refine our understanding and pushes the boundaries of what we know. Despite these advances, there are still many unanswered questions about the era of reionization. For example, what were the dominant sources of ionizing radiation during this period? How did different types of galaxies contribute to reionization, and how did their environments shape their evolution? What role did exotic phenomena, like population 3 stars and early black holes, play in this process? Answering these questions will require not only more observations but also a deeper theoretical understanding of the complex interactions that govern the early universe. The search for answers is not just an academic exercise, it is a journey of discovery that connects us to the cosmos in profound ways. By studying the era of reionization, we are exploring a time when the universe was young, vibrant, and full of potential. It was a time when light returned to the cosmos, revealing the first glimpses of the structures that would eventually lead to galaxies, stars, planets, and even life itself. Every step we take toward understanding this epoch brings us closer to answering some of the most fundamental questions about our existence. Where did we come from? How did the universe become the way it is today? And what can the distant past tell us about the future of the cosmos? These are questions that have inspired humanity for centuries, and they continue to drive our exploration of the universe. In many ways, the era of reionization is a mirror of our own curiosity, a time when the universe itself was awakening, full of questions and possibilities. As we delve deeper into this epoch, we are not just uncovering the secrets of the past, we are also laying the groundwork for future discoveries. The light that began to shine during reionization has traveled billions of years to reach us, carrying with it the story of the cosmos. It is a story of beginnings, of transformation, and of the enduring power of light to illuminate even the darkest corners of existence. The era of reionization is also an era of contrasts, a delicate interplay of forces that reveals the struggle between creation and destruction. The radiation that illuminated the cosmos after the Dark Ages did not simply bathe the universe in light. It also had profound and often destructive effects on its surroundings. This balance between light and darkness, creation and annihilation, is a recurring theme in cosmic history and one that was especially prominent during reionization. The process of ionization itself was transformative but violent. When the first stars ignited, their ultraviolet radiation began stripping electrons from surrounding hydrogen atoms. This ionization process heated the gas, increasing its pressure and preventing it from collapsing into new stars. In this way, the very light that heralded the end of the cosmic dark ages also acted as a brake on the formation of new celestial bodies. This paradoxical effect, known as radiative feedback, has profound implications for our understanding of galaxy formation. Radiative feedback likely created a patchwork effect, where regions of space near early galaxies and stars became ionized while more distant regions remained neutral. Over time, these ionized regions expanded and merged, creating the large-scale structures we observe in the universe today. However, the heating caused by radiative feedback may have also suppressed the formation of smaller galaxies, limiting their growth and altering the overall distribution of matter in the cosmos. Understanding this interplay between heating, cooling, and star formation remains one of the key challenges in the study of reionization. At the same time, the era of reionization was marked by the growth of large-scale structures such as cosmic filaments and voids. These structures, shaped by the gravitational pull of dark matter, provided the scaffolding for the universe's evolution. As gas flowed along these filaments, it fueled the formation of galaxies and galaxy clusters, creating a cosmic web that spanned billions of light years. The ionizing radiation from stars and galaxies followed these same filaments, carving out pathways of light that illuminated the universe's structure. One particularly intriguing aspect of reionization is the role of metal enrichment in the intergalactic medium. When the first stars ended their lives in supernova explosions, they ejected heavy elements, or metals, into the surrounding gas. These metals acted as catalysts for cooling, enabling the gas to condense and form new stars more efficiently. The presence of metals also influenced the chemistry of the intergalactic medium, leading to the formation of molecules like carbon monoxide and hydrogen deuteride. Observing these molecules in distant galaxies provides valuable clues about the chemical evolution of the universe during reionization. The transition from a neutral to an ionized universe also had profound effects on the visibility of distant objects. During the Dark Ages, neutral hydrogen absorbed much of the light from early stars and galaxies, making them difficult to observe. As the universe became ionized, this absorption diminished, allowing more light to escape and travel across vast distances. This increased transparency opened a window into the early universe, enabling us to study galaxies that formed during this pivotal era. However, it also created challenges for astronomers, as the faint light from these distant objects is often obscured by intervening material. One of the most powerful tools for studying the era of reionization is the observation of the Lyman alpha emission line, a spectral feature produced by hydrogen atoms. This line is a key tracer of star formation and ionization, as it is emitted when electrons and hydrogen atoms transition between energy levels. Observing Lyman alpha emission from distant galaxies provides a direct measure of their star-forming activity and the state of the surrounding medium. However, the detection of this emission is complicated by the presence of neutral hydrogen, which absorbs Lyman alpha photons and creates gaps in the observed spectra. As we look deeper into the cosmos, we are also beginning to explore the role of dark matter during reionization. While dark matter does not emit or absorb light, its gravitational influence shaped the distribution of gas and stars in the early universe. The clumping of dark matter into halos provided the seeds for galaxy formation, while its overall distribution influenced the large-scale structure of the cosmos. Studying the interactions between dark matter, gas, and radiation during reionization offers new insights into the fundamental nature of the universe. The era of reionization is not just a chapter in cosmic history, it is a key to understanding the universe's evolution as a whole. By studying this epoch, we can trace the origins of the structures we see today, from galaxies and clusters to the cosmic web itself. We can also uncover the processes that shape the distribution of matter and energy, providing a foundation for future discoveries. Perhaps most importantly, the era of reionization reminds us of the interconnectedness of all things. The light from the first stars and galaxies traveled across vast distances to reach us, carrying with it a message from the past. It tells a story of transformation, resilience, and the enduring power of light to illuminate even the darkest corners of existence. As we continue to explore this epoch, we are not just uncovering the secrets of the universe, we are also discovering our place within it. The quest to understand reionization is far from over. New telescopes, such as the Square Kilometre Array and the Extremely Large Telescope, promise to push the boundaries of what we can observe, revealing even more about this fascinating era. These instruments will allow us to probe the faintest and most distant galaxies, map the distribution of neutral and ionized gas, and uncover the intricate interplay between radiation and matter. Together with theoretical models and simulations, these observations will bring us closer to answering the fundamental questions that drive our exploration of the cosmos. The story of the era of reionization is a testament to the power of curiosity and the enduring human desire to understand the universe. It is a story of light returning to the cosmos, illuminating the path forward and inspiring us to look deeper, think bigger, and dream of what lies beyond. In many ways, it is a story that mirrors our own journey, a journey of discovery, growth, and the search for meaning in a vast and mysterious universe. The exploration of the era of reionization reveals a tapestry of interconnected processes, each influencing the universe's transformation from darkness to light. At its core, this epoch showcases the delicate balance between forces that either promote or inhibit cosmic evolution, and the interplay of matter, energy, and time. One particularly fascinating aspect of this period is the duality of its effects on smaller and larger structures within the universe. While radiative feedback from the first stars suppressed star formation in smaller halos, it also enabled larger galaxies to dominate their surroundings. This competitive dynamic between small and large structures highlights the hierarchical nature of cosmic evolution, a process where small-scale systems are often sacrificed to fuel the growth of larger ones. Additionally, the ionization of the universe was not instantaneous but occurred over hundreds of millions of years, forming ionization fronts that swept across space. These fronts were driven by clusters of early galaxies, whose combined radiation carved out massive ionized bubbles. The movement of these fronts was influenced by the distribution of matter, creating a patchwork of ionized and neutral regions. Observing these fronts allows us to piece together the timeline of reionization, revealing when different parts of the universe transition from darkness to light. The interaction between radiation and the intergalactic medium, IgM, during reionization also played a significant role in shaping the universe's future. The heating caused by ionizing radiation increased the pressure of the IgM, which in turn affected the motion and collapse of gas clouds. This heating also created temperature fluctuations across the cosmos, with some regions becoming warmer and more resistant to gravitational collapse. These thermal processes had a long-lasting impact, influencing the rate of star formation and the distribution of galaxies even after reionization ended. As we delve deeper into this epoch, another critical element emerges: the influence of black holes. The first black holes likely formed from the collapse of massive stars, and their growth through accretion generated intense radiation. These early black holes, known as quasars, acted as beacons in the distant universe, providing some of the brightest sources of light during reionization. Their energetic outflows also contributed to heating and ionizing the surrounding gas, playing a dual role in shaping the early universe. Quasars are particularly valuable to modern astronomers because their light acts as a probe of the IgM. As the light from a quasar travels across space, it interacts with the intervening gas, leaving imprints in its spectrum. By analyzing these imprints, we can map the distribution of neutral and ionized gas, identify the locations of ionization fronts, and even infer the chemical composition of the IgM. This information helps us reconstruct the history of reionization and understand the environments in which the first galaxies formed. Equally important are the role and influence of supernovae during this time. The first generations of massive stars likely ended their lives in spectacular explosions, releasing vast amounts of energy and enriching their surroundings with heavy elements. These supernovae also generated powerful shock waves that compressed nearby gas, potentially triggering the formation of new stars. At the same time, the ejected metals altered the cooling properties of the IgM, enabling more efficient star formation in subsequent generations. This feedback cycle of star formation and supernova explosions contributed to the rapid evolution of galaxies during reionization. Understanding the chemistry of the era of reionization requires a closer look at the creation of molecular hydrogen. Although atomic hydrogen dominated the universe during the Dark Ages, the first stars produced ultraviolet light that catalyzed the formation of molecular hydrogen. This molecule became a crucial coolant, allowing gas to condense into the dense regions where new stars formed. Observing the remnants of these early chemical processes in today's universe provides a direct link to the conditions that existed during reionization. The observational challenges of studying reionization are immense, yet advancements in technology and methodology have brought us closer to unraveling its mysteries. One of the most promising techniques is 21 cm line observation, a method that detects the radio waves emitted by neutral hydrogen. By mapping these emissions, scientists can trace the distribution of neutral and ionized gas, revealing the structure and progression of reionization. Upcoming instruments like the Hydrogen Epoch of Reionization Array, HERA, and the Square Kilometer Array, SKA, promise to revolutionize this field, offering unprecedented detail about the early universe. Another groundbreaking approach involves gravitational lensing, which uses the bending of light by massive objects to magnify distant galaxies. This technique allows us to observe galaxies that would otherwise be too faint to detect, providing a glimpse into the small, primordial structures that drove reionization. Coupled with deep field imaging from telescopes like the James Webb Space Telescope, JWST, gravitational lensing is opening new windows into the earliest epochs of cosmic history. The combination of observational data and theoretical modeling is crucial for piecing together the story of reionization. Simulations that incorporate the effects of gravity, radiation, and chemistry are helping scientists explore how galaxies formed and interacted with their surroundings during this time. These models also allow researchers to test different scenarios for the sources and timing of reionization, refining our understanding of this complex process. As we contemplate the era of reionization, we are reminded of the incredible journey that light undertook to illuminate the universe. From the first flickers of starlight to the sweeping ionization fronts, this epoch represents a turning point in cosmic history. It was a time when the universe transitioned from simplicity to complexity, from darkness to light, and from isolation to interconnectedness. Each photon of light carried with it the imprint of its origins, a testament to the processes that shaped the cosmos. The era of reionization is not just a window into the past, it is a guide to understanding the future. The structures and processes that emerged during this time laid the foundation for the universe as we know it, influencing everything from the distribution of galaxies to the evolution of life. By studying this epoch, we are not only uncovering the secrets of our cosmic origins, but also gaining insight into the forces that will shape the universe's destiny. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.